What was there before the Big Bang? You close your eyes and try to picture it. A time before time. A place before space. The silence is absolute, not the quiet of a room or the stillness of night, but a true void. No stars, no atoms, no moments ticking forward, just nothing. Or so we think. The Big Bang wasn't an explosion in space, or it was the birth of space itself. Everything we know, matter, energy, the very fabric of time, all emerged from that single, infinitesimal point. But here's the unsettling truth. The concept of before may not even apply. Time began with the Big Bang. So asking what came before is like asking what's north of the North Pole. Still, your mind resists that. It aches for a before. Was it an eternal void? A quantum field simmering with chaotic energy? Or another universe collapsing in on itself, triggering ours like a cosmic heartbeat? Some theories suggest a big bounce, an infinite cycle of universes expanding and contracting like lungs inhaling and exhaling through eternity. Others lean into quantum mechanics, where particles pop in and out of existence even in a vacuum. Could our entire universe be one of those fluctuations? A temporary anomaly in a grander, unknowable reality? And then there's string theory, whispering of higher dimensions and brains colliding, each crash birthing a new cosmos. In this view, our Big Bang wasn't a beginning, just the latest ripple in an ocean far deeper than we can imagine. But every theory runs into a wall. A limit to our equations, a horizon we can't see beyond. Because every telescope, every particle accelerator, every whisper of evidence begins after that first instant. The true origin remains cloaked in mathematical fog. And yet, you wonder, what if nothing isn't really nothing? What if our definition of before is simply wrong? A product of brains wired to understand time as a line instead of a loop, or a web, or something stranger still. Maybe we're like goldfish in a bowl, trying to understand the ocean. Or maybe the very question itself holds the key, not to physics, but to perspective. In seeking a beginning, we reveal our own need for meaning, our need for anchors, for stories that start somewhere and go somewhere else. But the universe may not owe us a beginning. It may not owe us answers. Still, as you sit with the weight of that question, something stirs in the darkness, a feeling not of despair but of wonder, of awe at a mystery so vast, so perfect in its refusal to be solved, that the question itself becomes sacred. So what was there before the Big Bang? Maybe not a place, maybe not a time. Just a question, waiting to be asked. Why is the universe expanding faster and faster? You gaze into the night sky, expecting stillness, a frozen portrait of distant stars. But the truth is far more disturbing. The universe isn't static, it's stretching, growing. Galaxies are racing away from each other, not slowly, but faster with every passing second. And no one knows exactly why. It began with a surprise. In 1998, two teams of astronomers studying distant supernovae stumbled upon a revelation. These exploding stars weren't just far, they were too far. The light reaching Earth was dimmer than expected, which meant one thing: the universe's expansion was accelerating. That was the opposite of what we thought. Gravity, the great cosmic glue, should be slowing everything down, like tossing a ball into the air and watching it fall. But instead, the universe was speeding up, as if some invisible hand was pushing it apart. That hand we now call dark energy. It's a haunting name because we don't know what it is. It isn't matter, it isn't radiation, it doesn't clump or collide or light up the sky. It's just there, woven into the fabric of space itself, and it's powerful. Today, dark energy makes up about 68% of everything. Not stars, not dust, just this invisible pressure. The more the universe expands, the more space there is. And with more space comes more dark energy. It's a feedback loop, a runaway engine. Galaxies drift farther, and that drifting only accelerates. Someday, distant galaxies will slip beyond our view entirely. Their light stretched so thin by expansion, it will never reach us. Some physicists fear it won't stop there. There's a theory called the Big Rip, a future where dark energy grows stronger and stronger until it tears galaxies apart. Then solar systems. Then atoms. Even the very structure of space, everything reduced to shreds, not with a bang, but with a final, silent unraveling. And yet others believe the acceleration could slow, or shift, or even reverse, that we might be witnessing just one act in a cosmic play with unknown rules, a temporary phase, a passing breath. So, what is driving this expansion? Is it a hidden field we haven't discovered? A property of quantum vacuum energy? Or a flaw in our understanding of gravity itself? Each answer only leads to deeper questions. Why now? Why did this acceleration start billions of years after the Big Bang, not before, not later, but in the cosmic moment when humans began to look up and ask? Coincidence? Or is our presence somehow connected? You feel a chill as you realize we're not just watching the universe change. We're inside it, carried along by a force we can't see, understand, or stop. It's a strange kind of motion. Silent, invisible, eternal. The stars drift apart. The night grows colder, and the mystery pulls tighter. So, why is the universe expanding faster and faster? Because space itself is restless. And maybe so are we. What is dark matter made of? You look up and see stars, shimmering, brilliant, scattered across the black canvas of night. But what you don't see is far more important. Most of the universe is missing. Not in the sense of being gone, but invisible, untouchable, undetectable by light. We call it dark matter, a silent, unseen substance that outweighs everything we can see. Galaxies spin too fast, stars on their edges orbit far quicker than gravity should allow. By all logic, they should fly apart, but they don't. Something is holding them together. That something we can't see. Imagine watching a carousel from a distance. The horses move faster than the supports can handle, but it stays together. You can't see the extra beams hidden beneath, but you know they're there. Dark matter is that hidden support, the invisible scaffolding of the cosmos. And yet, despite its influence, we've never touched it, never seen it. It doesn't glow, it doesn't absorb, it doesn't collide or clump or interact with normal matter, except through gravity. It's like a ghost that holds galaxies in its hands. So, what is it? Some believe it's made of WIMPs, weakly interacting massive particles, heavy, slow, and silent. Billions may pass through your body every second without a trace. We've built underground detectors shielded from radiation, waiting for a whisper of contact. So far, nothing. Others suspect axions, feather-light particles born in the early universe. Or even sterile neutrinos, a mysterious cousin of the neutrinos we know, slipping through dimensions just out of reach. And then, there are stranger ideas. Maybe dark matter isn't made of particles at all. Maybe it's a quirk of gravity, a flaw in Einstein's equations that only appears on galactic scales. Modified gravity, some call it. Not something added to space, but something strange about space itself. Or perhaps dark matter lurks in hidden dimensions, curled up too small to see, influencing us from the shadows. A parallel universe brushing against ours, leaving only gravity behind. We've mapped its effects with stunning precision. We can see where it clumps, where it pulls, how it shaped the early universe like an invisible hand molding clay. But the substance itself remains silent. Why? Is it too weak, too strange, or are we simply not asking the right questions? you sit with that silence, a cosmic silence that blankets everything. You begin to understand that the universe we see is just a thin skin on something much deeper, much darker, and far more mysterious. We chase the shadow of dark matter like an echo in a cave. We see what it moves, but not what it is, and yet we keep asking, because somewhere, hidden in the night, is the answer. So what is dark matter made of? Maybe it's matter we haven't met yet, or maybe it's a reminder that not everything real can be seen. What is dark energy really doing? You stretch your hand into the air, feeling nothing but stillness. But out there, far beyond your reach, something is moving. Something is pushing. Not with sound or force, but with expansion. A silent pressure, stretching the universe itself wider and wider, faster and faster. We call it dark energy. But truthfully, we don't know what it is. It doesn't shine. It doesn't weigh. It doesn't collide or curve or collect. It doesn't act like any substance we've ever known. Yet somehow, this invisible thing makes up nearly 70% of the universe. Not stars, not gas, not dark matter, just this. It was discovered by accident. In the late 1990s, scientists were measuring the brightness of ancient supernovae, cosmic explosions from far-off galaxies. They expected to see signs of slowing, as gravity pulled everything back together. But instead, the light was too dim. Too far. The expansion wasn't slowing, or it was accelerating. The universe wasn't just stretching, it was being pushed apart. And dark energy, whatever it is the prime suspect. But what is it doing, really? Some believe dark energy is a constant, a built-in pressure of space itself. Wherever there is vacuum, there is dark energy. As the universe expands and creates more space, more dark energy appears, which causes even faster expansion. A loop, a runaway engine. Others believe it's a dynamic field, changing over time. What we see now might just be one moment in a shifting cosmic tide. One day, it might grow stronger, or vanish completely. That would mean everything we know about cosmic fate could change. And then there are those who think we're only scratching the surface. That dark energy is a symptom, not a cause, a sign that our understanding of gravity or even space-time itself is incomplete. Could it be leaking in from another universe? Could it be the footprint of higher dimensions pressing in on ours? Or a relic of some ancient phase shift, like ice turning into water in the first moments of creation? Whatever it is, dark energy is shaping our future. If it continues unchecked, galaxies will drift beyond view. Stars will vanish. Eventually, the night sky could go dark, not from extinction but from distance. Light will no longer reach us. Some say this will lead to the heat death of the universe, a cold, flat, lightless emptiness. Others fear the Big Rip, where even atoms will be torn apart. But maybe dark energy isn't an ending. Maybe it's a key, a message hidden in the fabric of existence, a clue that the universe is more than it seems, not just matter and motion, but mystery and meaning. So what is dark energy really doing? It's whispering across the void, telling us that space is not still, that the cosmos is alive, shifting, evolving, and that some forces don't need to be seen to shape everything. Is the universe infinite or just very big? You stare into the night sky and it feels endless. Stars scatter in every direction, no edge, no wall, no boundary. But is that just an illusion? Is the universe truly infinite, or simply so vast our minds can't grasp its size? The truth is, we don't know. Infinity is a powerful word. It doesn't just mean really big. It means without end. No final galaxy, no furthest star, no outer shell or edge, just more. Always more, in every direction. But here's the strange part. We can only see a tiny piece of it. The observable universe stretches about 93 billion light-years across. That's the distance light has managed to travel since the Big Bang, given the stretching of space. Everything beyond that? Hidden, forever out of reach. The light hasn't had time to get here, and maybe never will. So the question becomes, is there something beyond what we can observe? Or does space simply stop? Cosmologists lean toward the idea that the universe has no edge, that if you could fly in a straight line forever, you'd never hit a wall. You'd just keep going. But that doesn't necessarily mean it's infinite. Some models suggest the universe is finite but unbounded, like the surface of a sphere but in more dimensions. Imagine a two-dimensional creature walking on a globe. It never hits a wall, but its world loops back on itself. Could our three-dimensional space work the same way? Others argue that space is truly infinite, stretching without end, filled with galaxies beyond count. Perhaps even endless copies of us living out nearly identical lives in far-off regions we'll never reach. But if it is infinite, that leads to strange consequences. In an infinite universe, everything that can happen will happen. Somewhere. Every possible arrangement of atoms, every version of Earth, every alternate you would exist out there, repeated an infinite number of times. It's a dizzying thought, and yet we have no way to measure infinity. We can map the curvature of space, look for patterns in the cosmic microwave background, test whether the universe is flat, curved, or closed. So far, the data says it's flat within a margin of error, and a flat universe could be infinite, or just very, very big. The difference: one is a mathematical concept that never ends, the other is a boundary we may never find, not because it isn't there, but because we'll never reach it. So, is the universe infinite? Maybe, or maybe our idea of size breaks down at this scale. Maybe we're asking the wrong question. Maybe it's not about how big the universe is, but how big our understanding needs to become. You look back at the sky, and suddenly, even the silence feels enormous. Are we living in a multiverse? You wake up, stretch, and go about your day. Everything feels normal, real, solid. But what if this version of reality, the one you know, is just one among countless others? What if there are infinite versions of you living slightly different lives in parallel worlds you'll never see? Welcome to the multiverse. It's not just science fiction anymore. The idea that our universe might be one bubble in a vast cosmic foam has slipped from comic books into real theoretical physics. Not because we want it to be true, but because some of our best scientific models suggest it might be. Let's start with inflation. Not economic inflation, but cosmic inflation, the rapid expansion of space right after the Big Bang. Some versions of this theory suggest inflation never truly ends. It just slows down in some places, forming bubbles. Each bubble becomes its own universe. Ours is just one. And what's inside these other bubbles? Anything. Maybe the laws of physics are different. Maybe gravity is weaker or stronger. Maybe stars don't form, or life can't exist. Or maybe they look a lot like ours. But history took a different turn. Then there's quantum mechanics. At its core, it tells us particles don't have one state. They exist in many states at once until observed. One interpretation, the many worlds theory, says every possible outcome actually happens in a different universe. Flip a coin, and in another world, it lands the other way. You chose tea? Somewhere else it was coffee. Every decision, every possibility, all real somewhere. And string theory? It doesn't stop at particles and forces. It needs more dimensions than we can see. Some versions suggest our universe is a three-dimensional brain, floating in a higher dimensional space, brushing against other brains, other universes just beyond our reach. But if the multiverse is real, how would we ever know? We can't visit these other worlds. We can't talk to their versions of us. They might be separated by vast gulfs of space, or folded in dimensions we can't perceive. Even detecting them indirectly, through faint patterns in the cosmic microwave background or gravitational waves, would be a miracle of science. And yet, something about the idea sticks. Because it might explain why our universe seems so perfectly tuned for life, why the constants of nature are just right. In a multiverse, most universes don't support life, but we find ourselves in one that does, not because it's special, but because we're here to ask. So, are we living in a multiverse? Maybe, maybe not. But the question itself reshapes how you see reality. Suddenly your world feels both smaller and infinitely vast, a single thread in a cosmic tapestry of endless possibility. And somewhere, out there in the dark, another version of you is wondering the same thing. What happens inside a black hole? You stand at the edge of the abyss, a place where space itself falls inward. Before you is the mouth of a black hole, vast and silent, surrounded by twisted light and shredded time. One step forward and the laws of physics begin to unravel, so what happens inside? A black hole isn't just a dead star. It's a region of space where gravity becomes so intense that nothing, not even light, can escape. The boundary is called the event horizon. Once something crosses it, there's no going back, no signal, no scream, no return. But beyond that horizon lies mystery. At first, things don't seem so strange. As you fall, you might not even notice the exact moment you cross the event horizon. The outside world disappears, time distorts, and space stretches. To an observer watching from afar, you seem frozen in place, forever hovering at the edge. But to you, the fall continues. Faster, deeper, stranger. Gravity grows stronger with every heartbeat. Space warps inward. Time slows down. Eventually, you approach the singularity, the center of the black hole. A point of infinite density, where the curvature of space-time becomes infinite. All known physics breaks down. At the singularity, all paths lead inward. Every direction becomes the same direction. Down. Your fate is sealed. And yet, we don't really know what's there. Some believe it's the end of space and time, a final stop. Others suggest the singularity is a window, a tunnel to another universe, a wormhole hidden in gravitational armor. But even that idea is more hope than certainty. Here's the real problem: general relativity, our theory of gravity, says one thing. Quantum mechanics, our theory of the tiny, says another. And inside a black hole, both theories collide. Relativity predicts a smooth fall into a singularity. Quantum theory predicts chaos, particles popping, energy fluctuating, information preserved. They can't both be right. So physicists are searching for something deeper. A theory of quantum gravity that unites the two. Black holes may be the ultimate testing ground. And then there's the information paradox. If you throw something into a black hole, a book, a star, yourself, what happens to the information it contains? Is it lost forever? That would violate quantum theory. Some believe the information is encoded in the event horizon itself, a kind of cosmic hologram. Others think black holes slowly leak it back through faint radiation, known as Hawking radiation. But the truth, we don't know. No one has ever seen beyond the veil. So, what happens inside a black hole? Maybe it's the end of everything. Maybe it's a door to something else. Maybe it's the secret heart of the universe beating quietly in the dark. All we know is this: the closer we look, the deeper the mystery becomes. And somewhere, out there, the black holes are waiting, silent, patient, and full of secrets. Do wormholes actually exist? You're drifting in deep space, surrounded by stars so distant they may as well be frozen. Suddenly, a tear, a hole, opens in the fabric of reality itself on the other side. A galaxy millions of light years away, close enough to touch. This is the dream of the wormhole. A shortcut through space, a tunnel between 2 points in the universe. Instead of taking thousands or millions of years to travel across the stars, you could step through a wormhole and arrive instantly, like folding a sheet of paper and punching a hole through it. But do wormholes actually exist? In theory, yes. Einstein's theory of general relativity doesn't just allow them, it predicts them. In 1935, Einstein and physicist Nathan Rosen proposed what's now called the Einstein-Rosen bridge, a mathematical solution where 2 points in space could be connected by a tunnel. But there's a catch. Several, actually. First, natural wormholes, if they do exist, would likely be unstable. They'd collapse before anything, even light, could pass through. Like a tunnel made of fog, gone before you can step inside. To hold a wormhole open, you'd need something called exotic matter, a substance with negative energy density. Not just rare, something we've never seen in nature. It would push space outward, counteracting gravity and keeping the tunnel from caving in. Without it, any attempt to pass through would end in crushing death. Still, the idea is tantalizing, because wormholes wouldn't just allow space travel, they could also be time machines. If one mouth moves faster than the other, say near a black hole, time would pass differently on each side. Step through and you might emerge in the past or the future. The implications. Terrifying or amazing. But, again, theory isn't reality. We've never seen a wormhole. No telescope has spotted a sudden blink of light across the cosmos. No strange warping of gravity that can't be explained by something else. And building one, even if we could find or create exotic matter, would require manipulating space-time itself on scales we can't begin to touch. Still, some physicists believe wormholes might exist naturally, hidden in the fabric of the universe, curled up at the quantum level, or floating through space undetected. Some even suggest that entangled particles, linked across distance, might be tiny wormholes in disguise. So what are we left with? A concept that's mathematically possible, physically elusive, and philosophically stunning. A doorway not just through distance, but through the limits of imagination. Do wormholes actually exist? We don't know. But the math says maybe. And the stars say, keep looking. Because somewhere out there, or maybe right here, folded between atoms, the universe might be hiding its greatest shortcuts. Waiting. Is time travel physically possible? You glance at the clock. Another second gone, another heartbeat passed. Time feels like a one-way road, always moving forward, never turning back. But what if that's not the whole story? What if time isn't a river, but a landscape? And what if you could travel it? The idea of time travel has fascinated humans for centuries. In fiction, it's a machine, a portal, a magic door. In physics, it's something stranger, and maybe, just maybe, possible. Let's start with what we know. Einstein's theory of relativity already allows for time travel into the future. The faster you move, the slower time flows for you compared to everyone else. This isn't science fiction. It's science fact. Astronauts on the International Space Station age just a little bit slower than we do on Earth. It's tiny, but real. Push this further, and it gets wild. If you traveled near the speed of light, time would slow dramatically. A journey that feels like days for you could mean decades back home. That's time travel forward. No paradox, no magic, just physics. But what about going backward? That's where the universe starts to frown. Some solutions to Einstein's equations suggest it's possible. Closed, time-like curves, loops in space-time, could, in theory, allow you to return to your own past. Wormholes, if they exist, might act as time bridges under the right conditions. But every attempt to make it work runs into the same problems. Paradoxes? The classic one? The grandfather paradox. If you travel back and prevent your grandfather from meeting your grandmother, you wouldn't be born. So who went back in time? Some physicists dodge this by suggesting time is self-consistent, that the universe won't allow contradictions. You can go back, but you can't change anything. Everything you do was already part of history. Others lean on the many worlds interpretation. Change the past? Fine. You create a new timeline, a parallel universe, branching away from your own. But even if we solve the paradoxes, we face another issue: energy. To bend space-time enough to make a time machine, you'd need negative energy or densities beyond anything we can produce. Some theories call for cosmic strings, rotating black holes or exotic matter, all far beyond our reach. So, is time travel physically possible? To the future, absolutely. We already do it in tiny amounts. With better technology, we might do more. To the past, it's murkier. The math allows it. The physics resists it. And the universe, so far, keeps its secrets well. Still, the idea lingers. In dreams, in stories, in the ticking of every clock. Because time travel isn't just about physics, it's about desire. To fix, to relive, to understand. To escape the arrow of time, even for a moment. And maybe, somewhere in the fabric of reality, that moment waits. Could the laws of physics be different elsewhere? You wake up in a universe that feels familiar. Light bends, gravity pulls, time ticks forward. But what if, somewhere far beyond the reach of our telescopes, none of that holds true? What if the rules we live by are just local customs? Could the laws of physics be different elsewhere? It's a mind-bending question, but one that scientists are beginning to take seriously. The laws we know, gravity, electromagnetism, nuclear forces, appear consistent everywhere we look. Whether we observe galaxies billions of light-years away or particles in a lab, the math seems to agree. But here's the thing. We've only seen a tiny portion of the universe. The observable cosmos, the part from which light has had time to reach us, is a cosmic island. Beyond that, a vast, unreachable ocean. And if the universe is infinite or part of a multiverse, then there's room for variation. Let's start with the constants. Numbers like the speed of light, the charge of the electron, or the strength of gravity seem fixed. But physicists wonder, why those values? Change them just slightly and stars don't form. Atoms fall apart. Life becomes impossible. This eerie fine-tuning has led some to suggest that our universe is just one of many, each with different constants, different laws. In some regions, gravity might be stronger, pulling everything into black holes. In others, it could be weaker, leaving matter to drift without ever forming galaxies. Maybe light moves at different speeds. Maybe time flows in loops. Maybe matter doesn't exist at all, only energy or patterns we can't imagine. String theory opens the door even wider. To make its math work, it proposes extra dimensions, curled up spaces we don't see. Depending on how those dimensions are shaped, the resulting universe could have entirely different physical laws. Our universe, then, might be just one possible configuration in a vast landscape of realities. But here's the twist. We can't test it. Not directly. These other realms, if they exist, may be forever beyond our reach. We're stuck observing the laws here, wondering about the laws there. Still, some clues might leak through. Tiny fluctuations in the cosmic microwave background, the afterglow of the Big Bang, might carry hints of interaction with other bubbles. And ongoing research into whether fundamental constants are truly constant could someday reveal a drift, a sign that even our own universe isn't as fixed as we thought. So, could the laws of physics be different elsewhere? Maybe. Maybe the universe is more like a quilt than a rule book. stitched together with patches of possibility. You stare into the sky, realizing we don't just live in a universe governed by laws. We live in a place that might be one way among many. And that makes everything, even the familiar, feel strange again. Is our universe just a simulation? You wake up, stretch your arms, feel the warmth of sunlight on your skin. Everything seems solid, real, undeniably physical. But a thought lingers in the back of your mind, unsettling, absurd, and yet impossible to ignore. What if none of this is real? What if the universe itself is a simulation? It sounds like science fiction, a plot from a movie. But in recent years, the simulation hypothesis has become a serious topic in both philosophy and physics. The idea is simple. Advanced civilizations, perhaps far older than ours, could have the computing power to simulate entire universes. Conscious beings inside such simulations wouldn't know the difference. And here we are, thinking, feeling, questioning. But how would we know if it's real? It started with philosopher Nick Bostrom, who proposed that at least one of the following must be true. Almost no advanced civilizations reach the level of technological maturity needed to run simulations. Advanced civilizations lose interest in running such simulations. We're almost certainly living in a simulation. If 1 and 2 are false, if it's possible and desirable to simulate universes, then statistically, simulated worlds would vastly outnumber real ones. And if that's the case, the odds we're in the one real universe? Almost zero. It's probability, not paranoia. But what would that mean? Some scientists have proposed we might detect the resolution of the simulation, like pixels in a game. Maybe there are limits to how small we can measure space or time. Maybe the Planck length is the universe's minimum pixel. Maybe quantum uncertainty is just the result of processing shortcuts. Others suggest there could be glitches, tiny inconsistencies in cosmic rays, or repeating patterns in the cosmic microwave background. So far, no smoking gun has appeared. But the strangeness of the universe fuels suspicion. Why does math describe reality so perfectly? Why is the universe so finely tuned for life? Why do particles behave unpredictably when observed as if responding to a script? Some even wonder if we're part of an experiment, a simulation built not for entertainment but for study. Maybe we're like ants in a glass farm, unaware of the eyes watching from beyond. And yet, there's something profoundly human about the question, because it touches our deepest fear, that reality isn't what it seems, that we are characters in a game and someone else holds the controller. But also, it touches our deepest hope, that there's something more, a layer beneath the world we know, a purpose to the simulation even if we can't see it. So, is our universe just a simulation? We don't know. Maybe we'll never know. But the very fact we can ask, that we want to know, might be the most real thing of all. Because even if we are simulated, the questions are ours, and they matter. What sparked the first galaxies into being? Imagine the universe in its infancy, dark, formless, silent. No stars, no galaxies, just a hot, dense fog of particles stretching in every direction. This is the cosmic dawn, a time before light, before structure, before anything familiar. And then, something changed. Tiny fluctuations in the sea of matter, random quantum ripples from the earliest moments after the Big Bang, began to grow. Ever so slowly, gravity took hold. It pulled matter together like invisible fingers gathering dust in a vast room. These clumps grew denser, heavier, warmer, and in the densest regions, hydrogen atoms collapsed under their own weight. Fusion ignited. The first stars were born. But they weren't like stars today. These were population 3 stars, giant, hot, and short-lived. They burned bright and fast, unleashing intense radiation across the cosmos. Their light pushed back the darkness, ending the cosmic dark ages. When they exploded, and many did as supernovae, they scattered the first heavy elements into space. Carbon, oxygen, iron, ingredients for planets, for life, for everything we know. The universe had taken its first breath of complexity. But it didn't stop there. These first stars formed in groups, gravitationally bound islands of light. Over time, their mutual gravity pulled more gas inward, attracting more stars, merging with other groups. These glowing clusters grew, collided, evolved. And just like that, the first galaxies began to emerge. They were messy, irregular, chaotic. Nothing like the elegant spirals and structured giants we see today. But they were the seeds, the ancestors of every galaxy in the night sky, including our own Milky Way. How long did this take? Surprisingly fast. Just a few 100 million years after the Big Bang, a blink on the cosmic timeline. By the time the universe was 1 billion years old, galaxies filled the sky. And what sparked it all? A perfect storm, gravity pulling, particles colliding, stars igniting, matter organizing. But also randomness, the tiny, uneven wrinkles in the early universe. Without them, nothing would have clumped. No stars, no galaxies, no us. We see this process frozen in time by looking far into space. The Hubble Space Telescope has captured images of ancient galaxies, small, glowing smudges from a time when the universe was still young. And newer telescopes, like James Webb, are peering even deeper, trying to catch the moment when the first galaxies flickered on. It's one of the greatest quests in modern astronomy, to understand how a cold, expanding cloud became a living sky. So, what sparked the first galaxies into being? Not a single explosion, not a magic switch, but a slow, chaotic, beautiful process, the universe learning how to shine. And in those first flickers of light, the blueprint for everything, from stars to planets to people, was written. Why does the universe seem so perfectly tuned for life? You breathe, your heart beats, you exist, balanced on the edge of cosmic precision. But look closer, and something strange becomes clear. The universe isn't just capable of life. It almost seems designed for it. Why? The universe runs on numbers, fundamental constants baked into reality. The strength of gravity, the mass of the electron, the rate at which the universe expands. These aren't random values, they're exact. So exact that if many of them were different by even a fraction, a hair's width in the math, life as we know it couldn't exist. If gravity were slightly stronger, stars would burn out too quickly. Slightly weaker, and they'd never ignite at all. If the nuclear force were just a bit off, the atoms in your body wouldn't hold together. If the cosmological constant, the energy driving the universe's expansion, were even a touch larger, space would tear apart before galaxies ever formed. Everything is just right. This is called the fine-tuning problem. It's one of the deepest puzzles in modern cosmology. Why is the universe so precisely arranged to allow the existence of stars, planets, chemistry, and us? Some say it's just luck, a cosmic lottery we happen to win. After all, we wouldn't be here asking the question if the answer weren't yes. This is known as the anthropic principle. The universe must appear fine-tuned because we're here to observe it. But others search for deeper meaning. One possibility? The multiverse. If there are countless universes, each with different physical constants, most would be barren, lifeless, chaotic, collapsed. But in one, this one, the numbers are right. Not by design, but by statistics. In the multiverse, life emerges not because the odds are good, but because they had infinite chances. Still, that answer feels unsatisfying. So some turn to intelligent design, the idea that some force, some intelligence, set the constants deliberately. Not science, but belief. It's not testable, but it echoes a deep human instinct to seek purpose behind precision. Then there's a more scientific hope that the fine-tuning is an illusion, that all these constants are connected, expressions of deeper laws we don't yet understand. Maybe they must be the values they are, the only self-consistent solution to a grand equation we've only glimpsed. In that view, the universe isn't a fluke. It's a necessity, and life, rather than rare, might be inevitable. So, why does the universe seem so perfectly tuned for life? Maybe it's a trick of perspective, maybe it's part of a grander pattern, or maybe it's the clearest clue that something astonishing lies beneath the surface. You look up at the stars and realize the universe didn't have to be this way. But it is. And that's the greatest mystery of all. Are there dimensions we can't perceive? You live in a world of length, width, and height. You walk forward, turn left, climb stairs, add time, the fourth dimension, and you get the flow of existence. It feels complete, full. But what if that's just a sliver of reality? What if there are more dimensions hidden from our senses? To most of us, dimensions are directions. Up, down, left, right, forward, back. But in physics, dimensions are much more. They're the framework of reality, the stage on which everything plays out. And some of the most advanced theories in science suggest that our universe may contain 10 or even 11 dimensions. It starts with string theory, the leading candidate for uniting quantum mechanics with gravity. In this theory, particles aren't tiny points, but tiny vibrating strings. Different vibrations create different particles, the same way guitar strings make different notes. But here's the catch. For the math to work, strings don't vibrate in just 3 dimensions of space. They need extra dimensions to resonate. Without them, the theory collapses. So where are they? Physicists believe these dimensions could be curled up, compacted into tiny shapes, far smaller than atoms, hidden in the fabric of space, like a garden hose from far away. It looks like a one-dimensional line, but up close, it has a circular shape. These extra dimensions might be real but too small to see or feel. Still, they could affect everything. The way particles behave, the strength of gravity, even the nature of dark matter or the birth of the universe. Some theories suggest gravity is weak because it leaks into these hidden dimensions. Others say entire parallel universes could be folded alongside us, just inches away but unreachable. And then there's M theory. It takes string theory further, proposing an 11th dimension and massive objects called brains. In this view, our entire universe could be a 3-dimensional brain floating in a higher dimensional space. Other brains, other universes, could exist nearby. We might even collide with one, triggering events like the Big Bang. It's wild, it's mathematical, and it might be real. But how do you prove it? Scientists are searching for signs, tiny shifts in gravity, particle behaviors that don't match predictions, patterns in the cosmic microwave background, hints that reality has more structure than we see. So far, the evidence is elusive. But the questions remain. Are we like flat creatures on a page, unaware of the third dimension above us? Could beings exist who see these extra dimensions, who move through them like we walk down a hallway? Or are these dimensions only mathematical scaffolding, real in theory, unreachable in fact? So, are there dimensions we can't perceive? Maybe. And if they're real, they're not just out there. They're here, all around us, woven into the very fabric of space, unseen, unfelt, but waiting. What lies beyond the observable universe? You stare into the night sky, through a telescope or with your bare eyes, and you see distance, depth, time itself. Light that left its source billions of years ago is only just reaching you. But no matter how far you look, there's a limit, a cosmic horizon. This is the observable universe. And beyond it, we don't know. We can't know. Not yet. The observable universe is not the whole universe. It's just the part we can see. Because light takes time to travel and the universe has only existed for 13.8 billion years, we're limited to what's had time to reach us. Add in cosmic expansion, and the radius of the observable universe balloons to about 46.5 billion light-years in every direction. Beyond that, it's not darkness, it's not empty space, it's simply unobservable. Light from those distant regions hasn't reached us yet, and some of it never will. But that doesn't mean there's nothing there. In fact, almost every model of cosmology suggests the universe continues, far beyond our sight. It could be hundreds of times larger. It could be infinite. Galaxies, stars, planets, entire structures may stretch on without end. There could be civilizations, cosmic events, even fundamental differences in how space behaves, all hidden just beyond the reach of light. And here's where things get stranger. If the universe is infinite, then beyond the observable edge lies not just more of the same, but every possibility. Every arrangement of matter, every configuration of atoms, including exact duplicates of Earth, of you, slightly different, wildly different. Universes where history branched in a million directions, not because of choice, but because infinity allows everything to happen somewhere. But even if the universe isn't infinite, it might still loop back on itself, like walking in a straight line and ending up where you started. That would mean if you could travel far enough beyond the horizon, you'd eventually come back to the beginning. And if that's not strange enough, there's the multiverse hypothesis, the idea that beyond our universe lies not just more space, but more universes, separate bubbles of reality, each with its own laws, its own particles, its own beginning. We'd be one drop in an endless sea of existences. But here's the mystery. We may never know. The observable universe is defined by light, and if something lies beyond that light, beyond the reach of our telescopes or particles, we are blind to it. No message can be sent, no probe can reach it. It's not just far away, it's causally disconnected, a place we can never touch. Still, we wonder, because the edge of the observable universe isn't a wall. It's a question, a reminder that the universe doesn't end where our sight does. So, what lies beyond the observable universe? Possibly everything. And maybe that's the most humbling truth of all. Where are all the aliens? Fermi paradox. You look up at the stars, thousands visible to the naked eye, billions more through telescopes. Around them, planets. Around those planets, life? The odds seem overwhelming. There are trillions of planets in the universe, many in the Goldilocks zone, not too hot, not too cold. So where is everybody? This is the heart of the Fermi paradox. In 1950, physicist Enrico Fermi posed a simple question during a casual lunch. Where is everybody? If intelligent life is common, why haven't we seen any signs? No signals, no spacecraft, no clear evidence, just silence. The paradox is chilling because the numbers say aliens should be everywhere. The Milky Way alone has over 100 billion stars. If even a tiny fraction have planets like Earth, and a smaller fraction developed intelligent life, there should be hundreds, maybe thousands of advanced civilizations in our galaxy right now. But we've found nothing. Why? Some answers are hopeful, others are terrifying. One possibility? We're early. Maybe intelligent life is still rare in the universe's timeline. Earth might just be among the first to arrive at this stage of development. In cosmic terms, we could be the pioneers, the first candle in the dark. Or perhaps alien civilizations are out there, but they're too far. even light takes years to cross the galaxy. Messages might take millennia to arrive, and if they sent one 1,000 years ago, we might still be waiting. Then there's the idea of different communication. Maybe we're listening on the wrong frequencies. Maybe aliens don't use radio at all. They could communicate using quantum entanglement, neutrinos, or methods we haven't even imagined. To them, our SETI efforts could be like shouting into a void using smoke signals. But what if they don't want to be found? The zoo hypothesis suggests advanced aliens are watching us, observing from a distance, letting us evolve without interference, like cosmic scientists studying primitive life. If true, we might be the ants in someone's backyard, unaware of the eyes above. And then there's the Great Filter. This is the darkest idea. Maybe intelligent life does emerge frequently, but something always wipes it out. War, environmental collapse, rogue AI. The filter could lie behind us or ahead of us. If it's ahead, it means most civilizations don't survive long enough to spread among the stars. That would mean the silence isn't mysterious, it's a warning. Still, there's one more possibility. We're alone, not just in the galaxy but in the entire visible universe. A fluke, a cosmic accident. If that's true, the responsibility is enormous, to protect life, to reach the stars, to be the voice in the silence. So, where are all the aliens? We don't know. But until we do, every message we send, every telescope we point outward carries the same hope, that somewhere, someday, the silence will speak back.